All right, welcome to the deep dive. Today, we're going deep, really deep, into the world of microprocessors.
Microprocessors, yeah.
You know, those tiny chips that make everything happen in our computers?
They're pretty important.
Understatement of the year.
And you've given us a mountain of incredible information, including some pretty intense excerpts from a textbook on Intel microprocessors.
It's dense stuff, but fascinating.
Absolutely. But, we're not aiming to drown you in technical jargon.
Definitely not.
Our mission here, and I think you'll agree, is to pull out the core concepts, the real aha moments that make you go, wow, that's how my computer actually works.
Exactly. We want to make it clear and engaging, even if you're not a computer engineer.
Right. So what kind of sources are we working with here?
We've got a really comprehensive technical resource that dives deep into the architecture, the programming, and even how these microprocessors interface with other components.
So it's not just about the chip itself, but how it talks to the rest of the computer. Precisely. And we're looking at a wide range of Intel microprocessors from the early 8086 to the more recent Core 2. We're talking about hardware interfaces, memory management, assembly language programming, that really low-level stuff.
The language the computer actually understands.
Exactly. And how all of that connects to the higher-level languages like C++, which is what a lot of software developers use today.
So it's like bridging the gap between the physical world of the chip and the more abstract world of software.
Right. And that's precisely what we're aiming to do in this deep dive. We want to paint a vivid picture of this intricate dance between hardware and software and highlight those key moments in the evolution of microprocessors.
The turning points that got us to where we are today.
Exactly. And along the way, we're going to showcase how those seemingly abstract programming concepts you might have heard of actually translate into real physical actions inside your machine.
So we're taking something incredibly complex and breaking it down into understandable and hopefully fascinating pieces.
And who knows, maybe even spark a few aha moments along the way.
So to really kick things off, let's travel back in time, way back.
To a time before microchips, before transistors, even before electricity was widely used.
You're talking about the very early days of computing.
And it might surprise you to learn that the very concept of a programmable computing machine dates back to the early 1800s.
Seriously, that early?
It's incredible, isn't it? The visionary behind this was Charles Babbage.
Okay, I've heard that name before.
And alongside him, Augusta Ada Byron, the Countess of Lovelace, played an absolutely crucial role. They were truly ahead of their time.
What were they working on exactly?
Babbage designed this amazing machine called the analytical engine.
And what was so special about it?
Well, picture this. A steam-powered mechanical computer.
Steam-powered, like a giant clanking, hissing machine.
Exactly. And this incredible contraption was intended to store 1,000 20-digit decimal numbers and execute programs just like the computers we have today.
That's wild. And how would you even program something like that?
Punched cards.
Punched cards, like those old things they used to use for voting.
Yes, exactly. Apparently, Babbage got the idea from Joseph Jacquard's loom, which used punched cards to control the patterns woven into fabric.
So the very idea of using physical objects to program a machine is a fascinating precursor to the digital world we live in today.
It is. And it really highlights that the fundamental concepts behind computing have been around for a surprisingly long time.
So fast forward about a century and a half, and we enter the electronic revolution.
A time of rapid advancements in electronics and a pivotal moment in the history of microprocessors.
And our sources highlight a major game changer, the Intel 80386.
The 80386, released in 1986. This was a groundbreaking achievement. It was Intel's first truly practical 32-bit microprocessor.
Okay, let's break down that 32-bit thing for a second. What made that such a big deal?
Well, imagine a data bus, the pathway that information travels on, as a highway. A wider highway, like a 32-lane highway compared to a 16-lane highway, can handle a lot more traffic at the same time.
So a 32-bit data bus allowed for much faster and more efficient data transfer.
Exactly. And it's not just the data bus. The 8386 also had a 32-bit memory address, meaning it could access a whopping 4 gigabytes of memory.
4 gigabytes. That was massive back then.
To put that into perspective, our sources tell us that 4GB could store something like 1 million typewritten double-spaced pages of text data.
That gives you a sense of the sheer scale of information it could handle.
And Intel didn't stop there. They continued to refine the 8386 architecture.
Oh yeah, they released a bunch of modified versions, right?
They did. Like the 8386SX, which could still address a substantial 16 millibit of RAM, and the 8386SLSLC, which could handle 32 millibit and even incorporated internal cache.
Cache? What's that?
Think of cache as a small, super fast scratch pad that sits right next to the processor. It holds the data the processor uses most frequently, so it doesn't have to go all the way to the slower main memory every time it needs something.
Ah, so it's like having the most important information right at your fingertips.
Exactly. And then in 1995, they released the 8386EX. This was so highly integrated, it had so many components of a typical PC all crammed onto a single chip that it was actually dubbed an embedded PC.
So it's essentially a whole computer on a single chip.
Pretty much. And this constant push toward more power and integration really fueled the incredible advancements we saw in personal computing.
Now, we've talked about processing power and how much information these microprocessors could handle, but how do they actually organize and access all that data?
Well, our sources dive into the world of memory organization. They explain that memory is often structured into segments.
Segments, like dividing a big bookshelf into different sections.
Exactly. And within each segment, there are offset addresses that pinpoint the exact location of specific pieces of data.
So it's like having a street address within a specific neighborhood.
A perfect analogy. And what's fascinating is that there are different addressing modes, different ways to find those addresses.
It's like different routes you could take to get to the same house.
Precisely. There's direct addressing, where you just specify the exact address you want.
Straight to the point.
Then there's register addressing, where you use a special storage location within the processor itself, called a register, to hold the address.
Okay, so it's like having a little note with the address written on it that you keep handy.
Exactly. And there are even more complex modes, like base plus index and scaled index addressing. These methods provide programmers with incredible flexibility in accessing data.
So you're saying that even seemingly simple instructions in a program can actually involve some pretty complex calculations to figure out these memory addresses.
That's right. A lot is going on behind the scenes that you might not even realize.
It's like the computer's doing all this invisible work to make things seem simple for us.
Exactly. And that's the beauty of abstraction in computer science.
Take scaled index addressing, for example. That's particularly clever for efficiently accessing elements within arrays.
Array.
You know, those ordered lists of data. Think of a shopping list. Each item is an element in an array.
Right, I get it.
And scaled index addressing makes it really efficient to find specific items in that list.
How does that work?
It takes the value in an index register. Think of that as a pointer to a specific item in the list, multiplies it by a scale factor, and then adds that result to a base address, which is like the starting point of the list in memory.
So you can jump right to the item you want without having to search through the whole list.
Exactly. And it's all done with a single efficient instruction.
That's pretty amazing. But we've been talking a lot about data. How does the microprocessor even understand what that data represents?
Well, that brings us to data representation, the fundamental way information is expressed at the core of a computer. And of course, it all boils down to binary numbers.
Ones and zeros.
The language computers speak.
And how do you represent something like a fraction using only ones and zeros?
That's where the binary point comes in. It's like the decimal point in our decimal system, but for binary. It separates the whole number part from the fractional part.
Interesting. And what about negative numbers?
That's where 2's complement comes in. It's a clever method computers use to represent negative numbers in a way that makes arithmetic operations much easier.
And our sources also cover how text is represented using character encodings like ASCII and Unicode.
Right, those are essentially dictionaries that map specific numbers to characters, symbols, and even emojis.
So when you type the letter A, your computer actually sees a specific number that represents that letter according to the encoding being used.
Exactly. It's how computers make sense of the text we create.
And at this really low level, assembly language often explicitly defines the size of the data being manipulated.
We're talking about directives like byte PTR, word PTR, and dear word PTR.
You'll see these sprinkled throughout assembly code.
And they tell the assembler, and ultimately the microprocessor, whether it's dealing with a single byte of data, which is 8 bits, a 16-bit word, or a 32-bit double word.
It highlights the incredible level of control programmers have at this level.
Speaking of assembly language, that's really the key to understanding what's going on inside the chip, isn't it?
Absolutely. It's the language the microprocessor directly understands.
And our sources provide a bunch of examples of assembly language instructions and how they directly manipulate the processor's internal registers and the computer's memory.
It can seem a bit cryptic at first, but it's fascinating to see how high-level code gets translated into these very basic machine instructions.
Let's take a simple example. Imagine a line of C++ code that says ntx y plus 4 3. Our sources show how this gets broken down into a sequence of assembly instructions.
You might see instructions to move the value of y into a register, add the number 4 to it, then move the number 3 into another register, perform the multiplication, and finally store the result back into the memory location representing the variable x.
It's like a step-by-step recipe for the microprocessor to follow.
And it really illustrates how those higher-level commands we use in languages like C++ are ultimately translated into these fundamental operations that the microprocessor can directly execute.
Now, we've been focusing a lot on the microprocessor itself, but it doesn't exist in isolation. It needs to communicate with the outside world.
That's where input-output, or I/O, comes into play. It's how the microprocessor interacts with peripherals, things like your keyboard, mouse, monitor, and storage devices.
Our sources talk about different I/O methods like pulled I/O and interrupt-driven I/O.
With pulled I/O, the microprocessor constantly checks if a device has data to send or needs attention. It's like repeatedly asking, "Are you ready yet? Are you ready yet?"
Not the most efficient way to do things.
No, it's not. That's where interrupt-driven I/O comes in. In this method, a device can signal the microprocessor directly when it's ready to communicate. It's like ringing a doorbell when you have something to deliver.
Much more efficient.
Absolutely. And our sources also mention the PC's I/O map. This is a fascinating concept.
What's the I/O map all about?
It's essentially a map that shows how specific port addresses, which are like numbered mailboxes, are dedicated to certain functions within the computer system.
So each device has its own unique address.
Precisely. And the microprocessor uses these addresses to communicate with the different devices.
And speaking of being responsive, let's talk about interrupts.
Interrupts are a crucial mechanism that allows the microprocessor to react quickly to events.
Instead of the processor constantly having to check every single device to see if it needs something, a device can just send an interrupt signal when it requires immediate attention.
Exactly. It's like raising your hand in class when you have a question.
And what happens when an interrupt occurs?
The microprocessor temporarily suspends whatever it's doing, saves its current state so it can resume later, and then jumps to a specific piece of code called an interrupt service routine to handle the request.
So it's like putting your current task on hold to deal with an urgent matter.
Precisely.
Okay.
And our sources explain the different types of interrupts, including hardware interrupts and software interrupts.
What's the difference?
Hardware interrupts are triggered by physical events, like pressing a key on your keyboard or a signal from a hard drive. Software interrupts are initiated by software instructions.
And the key takeaway here is that interrupts allow the microprocessor to respond quickly to events, which is essential for things like multitasking and real-time applications.
Absolutely. It's a fundamental concept in how modern operating systems and applications work.
Now let's shift gears and talk about high-speed data transfer, particularly when dealing with large amounts of data, like reading or writing files to a hard drive.
In those situations, constantly involving the CPU would create a bottleneck. That's where direct memory access, or DMA, comes in.
DMA. What's that all about?
DMA allows peripherals, like hard drive controllers or network cards, to directly access the system's main memory without needing the CPU to manage every single transfer.
So it's like giving those devices a special pass to access memory without bothering the CPU.
Exactly. And the 8237 DMA controller, which is mentioned in our sources, plays a key role in facilitating these high-speed transfers.
By offloading these data transfer tasks from the CPU, the overall system performance gets a significant boost.
The CPU is freed up to focus on other tasks, making everything run more smoothly.
And what about specialized mathematical calculations? I'm thinking of things like floating point arithmetic.
In the early days, computer systems often relied on a separate chip called an arithmetic coprocessor for those tasks.
Like the Intel 80x87 family mentioned in our sources.
Exactly. These coprocessors had their own set of registers and instructions specifically optimized for complex mathematical operations.
So it's like having a math whiz on hand to help with the heavy lifting.
A very apt analogy. And as microprocessors evolved, they incorporated technologies like SIMD.
SIMD.
Single instruction, multiple data. Think of it as a way to do parallel processing at the instruction level.
Parallel processing.
It means performing the same operation on multiple pieces of data simultaneously. Imagine a chef being able to chop multiple vegetables with a single knife stroke.
Ah, so it's about doing things more efficiently.
Precisely. And examples of SIMD technologies include MMX and SSE, which are mentioned in our sources. These technologies allow for significant performance gains, especially for things like multimedia applications.
So they're really important for things like video editing and image processing.
Absolutely. Now, we've talked about a lot of different components, the microprocessor, the memory, the peripherals, but how do they all communicate with each other?
That's where bus interfaces come in. They provide the pathways for data to travel between these components.
And our sources mention a variety of bus standards, both old and new. We're talking about ISA, PCI, AGP, SATA, and USB.
So many acronyms.
Each of these standards has its own characteristics, its own way of transmitting data, and they've evolved over time to keep up with the ever-increasing demands for speed and bandwidth.
It's like the evolution of transportation systems, from horse-drawn carriages to high-speed trains.
And understanding these different bus types gives you a better appreciation for how the various parts of a computer system work together.
Now, looking back at the evolution of microprocessors, it's really a story of constant innovation, isn't it?
It is. We've seen the shift from 16-bit to 32-bit architectures, the integration of cache memory, the development of specialized processing units, and the move towards multi-core processor.
Multi-core processors.
That's where you have multiple independent processors on a single chip. It's like having a team of chefs working together in a kitchen.
And our sources even mention hyper-threading, a technology that allows a single processor core to handle multiple tasks seemingly simultaneously.
It's a clever way to squeeze even more performance out of a single core.
And it seems like the future holds even more cores and even more processing power.
The pursuit of performance never ends.
So, for you, the listener, what are the key takeaways from this deep dive into the world of microprocessors?
Well, first and foremost, you should now have a much better grasp of the very foundation of computing. You've seen how the abstract world of software is built upon the very real physical operations of the microprocessor.
We started with those early mechanical concepts and traveled all the way to the sophisticated silicon chips we have today.
You've gained valuable insights into how memory is organized and accessed, how data is represented at its most basic level, and the crucial mechanisms that allow a computer to communicate both internally and externally.
And hopefully you had some of those aha moments along the way.
Maybe the realization that the concept of programmable computation predates even the electric light bulb surprised you.
Or perhaps seeing a simple line of C++ code translated into a series of basic assembly instructions gave you a new appreciation for the complexity that's hidden beneath the surface of your computer.
And the evolution from single-core to multi-core processors, and those clever techniques like SIMD for parallel processing, really highlight the relentless drive for ever-increasing performance.
Now, we've only scratched the surface in this deep dive. The world of microprocessors is vast and intricate.
You might now be curious about the specific functions of different assembly language instructions, the intricacies of memory management in modern operating systems, or the detailed design of those various bus architectures we mentioned.
And if you are, we encourage you to explore further. There's a wealth of information out there waiting to be discovered.
And feel free to send us your questions or suggest specific topics you'd like us to cover in Enhance Your Deep Dives.
We're always eager to delve deeper into the fascinating world of technology.
And before we wrap up, here's a final thought to ponder. Every line of code you write, every application you use, every interaction you have with your computer ultimately boils down to a sequence of very simple instructions executed by the microprocessor.
It's remarkable to think about the layers of abstraction that allow us to interact with such complex machinery in such intuitive ways.
And it makes you wonder what future innovations might fundamentally change this relationship between humans and computation.
It's a question worth pondering. Until next time, on The Deep Dive, keep exploring.
Keep learning.